Hello everyone. Today we are going to begin our lectures on trigonometric functions, which is chapter 4 of our textbook, and we are going to start with the first section of the chapter, which is on angles and radian measure. These are some of the topics that we are going to cover in this section. First of all, we are going to look deeply into angles, talk about the vocabulary. We all know what angles are. However, here we will try to look at angles from the perspective of geometry and trigonometry, look at the parts of an angle, and then we are going to talk about the different ways of measuring angles. There are two ways of measuring angles. We are familiar with angle measurements in degrees, for example, a 30-degree angle, a 60-degree angle, 90-degree angles, and so on. However, the units of measurement for angles can also be in radians, and that would represent the angle measure in terms of real numbers. And then we will learn how to convert from degrees to radians and from radians to degrees. We will talk about drawing angles in standard position. The standard position refers to drawing angles on a coordinate plane. We'll talk about coterminal angles, what they mean, and how we can identify coterminal angles. We'll talk about finding the length of a circular arc. Before that, we will understand what a circular arc is, and then we will talk about using linear and angular speed to describe motion on a circular path. Now we are going to begin with a formal definition of angles from the standpoint of geometry and trigonometry. Now whenever we think of angles, we picture it as two straight lines meeting at a common point, and the space or the gap between the two lines is what we know to be an angle. So that's the layman's view of an angle, and it's an absolutely correct idea of what an angle is. However, for purposes of getting deeper into the study of trigonometry, we need to look at angles at a more granular level. We need to know the different parts of an angle, how the different parts are labeled, the notations we use for the different parts, and so on. So here we have a detailed picture of an angle which is labeled and which has terminologies applied to the different part, and here we have the definition. So let's go through it. It says here an angle is formed by two rays that have a common end point. So what we know to be the two sides of the angle is also known as the two rays from a geometric point of view. All right, so here in this picture we see the blue ray labeled as ray AB, and then we have BC, the other ray. There has to be two rays to form an angle. We have ray BC as the second ray, and they meet at a common end point. So that point of intersection between the two rays is labeled as B, and it's also known as the vertex of the angle. All right, so the point where the two rays meet is known as the vertex, and the gap between the two rays is where the angle is, and it is denoted by the Greek letter theta. This particular symbol reads as theta, which is a Greek letter. We also use other Greek letters to denote angles. We also use alpha, this symbol here, which reads as alpha. So these are some of the notations. Now there are two other terms in this picture. We see the ray AB is known as the initial side, and it's called the initial side because that is the side from where the angle starts forming, and the other ray BC is known as the terminal side of the angle because that is where the angle terminates. That is where the angle comes to an end. It comes to a halt. It terminates. So think of the angle being created by moving the two rays. So think of initially BC and AB overlapping. They are located at the same position. So I'm going to draw a ray to represent BC. This red arrow that I just drew represents this BC. So I'm going to think that initially A, B, and B, C are located at the same position. They overlap. There's no space between them, so there's no angle formed at the initial position. And then gradually BC starts moving in the counterclockwise or anti-clockwise direction. So it keeps moving, and as it keeps moving, it starts forming an angle. And as it keeps moving, the angle becomes wider. The gap between the two rays become wider, and at some point it terminates, and that position is known as the terminal side. So wherever BC comes to a final halt, that side is known as the terminal side of the angle. So again, these are some of the terms that we must remember about angles. The initial side is the ray or the side from where the angle starts forming. The terminal side is the side where the angle comes to an end, where it terminates, and the point of intersection between the two rays is known as the vertex of the angle. Now in trigonometry, we frequently refer to angles in the standard position. So we need to understand what that is. The standard position of an angle occurs on the rectangular coordinate system. The rectangular coordinate system has a horizontal x-axis and a vertical y-axis, and they intersect at 0, 0, also known as the point of origin. The point of intersection between the x and the y axis is the point of origin marked by the coordinates 0, 0. Now an angle in the standard position on the rectangular plane has its vertex fixed at the point of origin at 0, 0. That's where the vertex of the angle is located, and the initial side of the angle lies on the positive x-axis, and it stays fixed there. It's the terminal side that moves about, either in the counterclockwise position as shown in this figure, right, in the first figure, or it can also move in the clockwise direction to form an angle as shown in the second figure. So the initial side stays fixed. It's the terminal side that moves around to form angles of different measures. And when the terminal side moves in the counterclockwise direction, it forms a positive angle, and if it moves in the clockwise direction, it forms a negative angle. So it says here an angle is in standard position if its vertex is at the origin of a rectangular coordinate system and its initial side lies along the positive x-axis. And I may also want to add that the initial side stays fixed along the x-axis. It's the terminal side that moves around either in the clockwise direction or an anti-clockwise direction to form an angle of a certain measure. So we already saw that angles in the standard position occur in the xy coordinate plane. Its vertex is at the point of origin and it has its initial side on the positive x-axis, and the initial side stays fixed. It's the terminal side that rotates in either a counterclockwise direction or a clockwise direction to form an angle. Now, when the rotation of the terminal side is in the counterclockwise direction, it forms a positive angle. If it rotates in the clockwise direction, it forms a negative angle. So how do we know the direction in which the terminal side is rotating? By looking at the arrow on the arc indicating the angle. So over here, this arc indicates the angle, and then here we see an arrow pointing to the terminal side. That indicates the direction of rotation is counterclockwise. In this picture, we see that the arrow pointing to the terminal side is moving in the clockwise direction. It indicates that the movement, the rotation is in the clockwise direction. We will now look into what a quadrantal angle is. Now, the x and y axis of the rectangular coordinate system divides the plane into 4 distinct regions, and we call each of these regions a quadrant. The quadrants can be numbered starting from the top right and moving in the counterclockwise direction. They can be numbered as quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Now, a quadrantal angle is formed when the terminal side rotates and comes to rest on the axis of the rectangular coordinate system. So it could come to rest on the positive y-axis or the negative x-axis or the negative y-axis, or even come all the way around and rest on the positive x-axis as well. So the angle that is formed when the terminal side lies on one of the axes is referred to as the quadrantal angle. So here it says an angle is called a quadrantal angle if its terminal side lies on the x-axis or on the y-axis. Angle beta is an example of a quadrantal angle in this figure. Let's review the different types of angles based on their angle measures. The first kind is the acute angle. Acute angles measure less than 90 degrees. So acute angles are rather narrow angles between the two rays, between the initial side and the terminal side. As long as the angles measure anything between 0 degrees and less than 90 degrees, they are considered to be acute angles. As soon as the angle becomes a 90-degree angle, they are known to be right angles. So right angles are those that measure exactly 90 degrees. Right angles are square angles, and the initial side and the terminal side in right angles are perpendicular to each other. The terminal side positions itself exactly vertical to the horizontal axis or the initial side of the angle. All right, so that's a right angle. Then we have the obtuse angle. They are angles that measure more than 90 degrees but less than 180 degrees. So they are kind of a wider angle, and they are angle measures that's greater than 90 degrees but less than 180 degrees. When the angle is 180 degrees, the initial side and the terminal side form a straight line. So here we have the initial side, and we know that the terminal side is the one that rotates about the vertex to form the angle, correct? So when the terminal side, so let me just draw the terminal side here with red, and when the terminal side rotates and positions itself in a straight line with the initial side, it forms a 180-degree angle. All right, so when the terminal side rotates and positions itself in a straight line with the initial side, it forms a 180-degree angle, and it's called a straight angle. And finally, we have the 360-degree angle, and that is formed when the terminal side completes a full circle and comes back to the position of the initial side. So whenever the terminal side comes around full circle to position in line with the initial side, it is a 360-degree angle. So a complete rotation of the circle is 360 degrees. Now let's talk about measuring angles using the units of radians. We already know that angles are measured in degrees. That's one unit of angle measurement. We are more familiar with angles being measured in degrees. However, there is another unit of measuring angles, and that is in radians. We have to understand what we mean by radians. But before that, we have to know what a central angle is. Now, an angle whose vertex is at the center of the circle is called a central angle. So I'm going to draw a circle here. It's not going to be a perfect circle, but let's just think this is the circle. Any circle has a center point, and the distance between the center point and the circumference of the circle, so this boundary around is the circumference, and the distance from the center point of the circle to the circumference is called the radius, denoted by the letter R. We can form angles using two radius of the circle, two radii of the circle, so to speak. So if I draw another radius from the center point to the circumference, then it forms an angle, correct? So this angle is what's called the central angle. So a central angle will always have its vertex at the center of the circle. That's the central angle. Now, the radian measure is the length of the intercepted arc divided by the circle's radius. What do we mean by the intercepted arc? Now, these two rays of the central angle, which is also the radius, intercepts a portion of the circumference of the circle. Correct? It intercepts this portion of the circumference of the circle, and that portion is called the intercepted arc. All right, so this portion of the circumference is also known as the intercepted arc, and that can be measured. The length of the intercepted arc divided by the length of the radius is the radian measure. The radian measure, in other words, is equal to the length of the intercepted arc, also denoted by the letter S, over R. So it's the ratio between the intercepted arc over the radius. So ratio of the arc and the radius, in other words. Now let's look at a formal definition of a radian. To define it, we'll try to understand what 1 radian is. 1 radian is the measure of the central angle of a circle that intercepts an arc equal in length to the radius of the circle. Let me try to explain that using this figure here. Again, we are talking about 1 radian. That means when the radian has a value of 1. Now, we learned previously that the formula for a radian is S over R, where S represents the intercepted arc between the initial side and the terminal side of the central angle. And S divided by R is what gives us the radian measure. Now, when would the value of the radian be equal to 1? Whenever S and R are equal to each other, correct? If they have the same value, then they will divide to give us 1 for an answer. So whenever S and R have the same measure of length, then we get 1 radian. So that's what they say here. 1 radian is the measure of the central angle of a circle that intercepts an arc which is equal in length to the radius of the circle. Here R denotes the radius and the arc normally is denoted by the letter S. However, when S is equal to R, equal to the radius, then it takes a value R. So whenever S has the same value as the radius of the circle, then we will end up with a radian value of 1. So let's summarize the definition of a radian measure and also look at the formula that we'll be using to calculate the measure of an angle in radians. Now, radian measures apply to central angles. In this figure, we see a picture of a central angle. The central angle has its vertex at the center of the circle, and the two sides of the central angle are the radius of the circle. Correct? This is the initial side and it will have a length of R, and then the terminal side, the distance from the center point to the circumference of the circle, would also be the radius, and then the angle in between the initial and the terminal side would be the central angle. Now, to calculate the measure of this angle in radians, we have to know the length of the arc intercepted by the initial and terminal sides of the angle, and we represent length of the intercepted arc with the letter S, and when we divide S by R, we get the measure of this angle in radians. We will now work on an example to calculate the radian measure of a central angle. Now the question here says a central angle theta in a circle of radius 12 feet intercepts an arc of length 42 feet. What is the radian measure of theta? Now, whenever we speak about radian measure, we refer to a central angle. And a central angle will always have its vertex at the center of a circle. So I'm going to draw central angle with its vertex at the center of this circle that I just pulled up. Let's draw here the central angle about the center of this circle, and then the two sides of the angle, the initial side and the terminal side, would be the radius of the circle. And recall that the radius of a circle is the same everywhere. Any distance from the center point of the circle to the circumference will always be the same, will always be equal. So we will mark these two sides as R, and R has a value of 12 as for the question. It has a value of 12 feet. The formula to calculate the radian measure of this central angle is S over R. So R is going to be 12 feet, we know that, but what is S? S is the distance between the two sides of the angle. In other words, it is the distance of the arc intercepted by the initial and the terminal side of the angle, and that distance is denoted by S. And the question tells us that the length of that intercepted arc is 42 feet. So we are going to plug in 42 feet for S. Radius is also in feet. We have to perform the division. Feet and feet divide, and 42 divided by 12 gives us a value of 3.5. Now note that the units in radian measure is lost. We do not put any units with the radian measure. Let's pull up the solution they have here. They start with the formula to calculate the radian measure and then plug in the values of S and R. S is 42 feet, R is 12 feet, and then feet and feet should cancel out. 42 divided by 12 is 3.5. So the radian measure of the central angle theta is 3.5 radians. All right. Now in the next couple of slides, we are going to learn how to convert between angle measures in degrees and radians. However, I want to explain the relationship between angle measures in degrees and radians because we'll be using that to perform the conversion. We'll start with a circle which has a radius of 1 unit. So here I pulled up a circle, and this circle has a radius of 1 unit. Now, the circumference of a circle can be measured using the formula 2 pi r. That's the formula to measure the circumference of any circle. 2 times pi times the radius. Now, if a circle has a radius equals 1, which is also called a unit circle, a circle whose radius is equal to 1, it's called a unit circle. So when radius equals 1, the circumference will have a value of 2 times pi times 1, therefore just 2 times pi. That's the measure of the circumference of a circle. Now let's think of a central angle of 180 degrees. We'll go back to angle measures in degrees and think of a central angle measuring 180 degrees. Now 180 degrees is a straight angle. That means it will be the angle formed by the diameter of a circle. So this angle here is 180 degrees. Now, the diameter of a circle divides circle into two equal parts, into two semicircles. So, if the entire circumference of the circle is 2 pi, then the portion of the circumference between the initial side and the terminal side of the 180-degree angle will be half of 2 pi, correct? It spans half the circumference. So it's going to be equivalent to half of 2 times pi, given that the radius is equal to 1. So we divide 2 and 2, and we will end up with 180 degrees being equal to pi. So 180 degrees is equivalent to pi radians. Given that relationship, we will work on converting from degrees to radians and radians to degrees. So then how do we go about converting angle measures from degrees to radians and vice versa? Now we've already established a relationship between degrees and radians, saying that 180 degree corresponds to pi radians. Therefore, 1 degree, and here I'm using the unitary method, so 1 degree would be pi over 180 degree. Therefore, any other angle measure, and I'm going to represent that with the variable x because it could take any other angle value. So x degrees would be calculated using the formula pi over 180 degree multiplied by x degrees, and then the degrees will cancel out and we will be left with an angle measure in radians. How do we convert from radians to degrees? Again, same process, except that I'm going to rewrite this initial relationship starting with pi. So pi radians corresponds to 180 degrees. I just reversed the positions here. Pi radians to 180 degrees, therefore 1 radian will be 180 degree over pi. 1 radian would be 180 over pi, therefore x radians will be calculated by using the formula 180 degrees over pi multiplied by x radians. So we're going to work on some examples next to apply this process. Now the first set of examples is to convert from degrees to radians, and we will start by converting a 60-degree angle to its radian equivalent. So I'm going to work it out myself first, and then I'm going to pull up the solutions to see if the answers match. So for the 60-degree angle, we'll start by building the relationship between the 180-degree angle and its radian equivalent, which is pi. So 180 degrees corresponds to pi radians, right? If we are converting degrees to radians, then you put the degrees on the left hand side. So 1 degree corresponds to pi over 180 degrees. Therefore, the 60-degree angle would be pi over 180 degrees multiplied by 60 degrees, which would be 60 over 180 pi. The degrees will cancel out and we will be left with pi over 3 radians. And you can leave the answer in terms of pi. You do not need to convert it to a real number. So let's pull up the solutions for the 60 degrees here. They've done pretty much the same thing. They followed the same steps. 60 multiplied by pi over 180 is exactly what we did here. And then they did the calculation. The degrees and degrees drop off and we are left with 60 pi over 180 radians, which will give us pi over 3 radians for the answer. For 270 degrees, they will follow the same process. So it would be 270 multiplied by pi over 180. It's 270 degrees multiplied by pi over 180 degrees. So we will have 270 pi divided by 180 degrees, which gives us 3 over 2 pi. So 3 pi divided by 2 radians is the answer. The negative 300 degrees. This is a negative angle. A negative angle is formed when the terminal side moves in the clockwise direction. When the angle is formed by moving in the clockwise direction, then it forms a negative angle. So negative 300 degrees multiplied by pi over 180 is negative 300 pi over 180, which gives us a value of negative 5 pi over 3 radians. So 300 pi over 180 has to be simplified, which gives us negative 5 pi over 3. Do not forget the negative sign, all right? Now let's work through some examples where we have to convert angle measures from radians to degrees. But first, let's build the conversion ratio by which we should multiply each of these radian measures to get our angle value in degrees. When we are converting from radians to degrees, we start with the radians on the left hand side. So pi is the equivalent of 180 degrees. So 1 radian is equivalent to 180 divided by pi. Again, I'm using the unitary method here. Therefore, x radians would be 180 degrees over pi multiplied by x. X being whatever radian measure we want to convert to degrees. All right. So the first example here says to convert pi over 4 radians. All we need to do is take this radian measure and multiply by the conversion ratio, which is 180 over pi. So I'm going to write it down here. So pi over 4 multiplied by 180 over pi, and then pi and pi should divide, and 180 divided by 4 is 45 degrees. So the angle measure in degrees for pi over 4 radians is 45 degrees. All right. So now I'm going to pull up the solution to see if that matches with what we got. All right. So again, they have pi over 4 radians multiplied by 180 over pi, which is the same as what we did, and then pi and pi should divide, radians should divide, so we'll have 180 degrees over 4, which should give us an angle value of 45 degrees. Now the next one is negative 4 pi over 3. This is a negative angle and they follow the same procedure. Just take the radian measure that you need to convert, multiply by the conversion ratio, which is 180 over pi, and just perform the multiplication there. So the way it's going to work is pi and pi will cancel out, radians will cancel out. 180 divided by 3 is 60 degrees. 60 times 4 is 240 degrees. However, this is a negative angle, so you must not forget the negative sign. We have to write our answer as negative 240 degrees. Right, so that's the angle measure in degrees for negative 4 pi over 3. The next one is 6 radians. The conversion ratio that you multiply 6 radians by is 180 over pi, and that should give us 6 times 180 degrees divided by pi. Radians and radians divide, and we should be left with an angle measure of approximately 343.8 degrees. All right, we are now going to learn how to draw angles in standard position. But before that, let's look at the radian measures of quadrantal angles. Now, what are quadrantal angles? They are formed when the terminal side moves from the initial side and comes to rest along either the x-axis or the y-axis. So it could move from the initial side and come to rest on the positive y-axis, or it could come to rest on the negative x-axis, or to the positive or on the negative y-axis, or it can come all the way around and position itself on the positive x-axis where it had started from initially. So when it makes one complete revolution or rotation, then it covers 2 times pi circumference of a unit circle. Recall what a unit circle is. A unit circle has a radius measure of 1 unit. Alright, so in that case, in a unit circle, the circumference of the circle is 2 times pi. So when terminal side makes a complete rotation, then it traverses a length of 2 pi. A circle in degrees has 360 degrees about it. So a 360-degree angle is also 2 pi in radian measure. The next one is when the terminal side comes to rest on the negative y-axis. In that case, it has made 3/4 of a rotation. It has come around 1, 2, 3/4, and it has come to rest on the negative y-axis. So it's 3/4 of 2 pi. So let's do that calculation. 3/4 of 2 pi, because 2 pi is the measure of the entire circumference of the unit circle. So 3/4 times 2 pi would give us 3/2 pi. Right? The next one is when it comes to rest on the negative x-axis. In that case, it has made half a rotation or half a revolution. It has covered half of a full circle. So in that case, it's 1/2 times 2 times pi. 2 and 2 divide, and we say that it has covered pi radians. For the 3/4 revolution, it was 3/2 pi. Right? And then finally, when it makes a 90-degree angle, in other words, when the terminal side comes to rest on the positive y-axis, it has made 1/4 of a revolution. Correct? So in that case, it would be 1/4 of 2 pi. 2 and 4 divide. So we are left with 1/2 pi or pi over 2. So a 90-degree angle is also in radian measures pi over 2. Now we are going to learn how to draw any angle in standard position. Now previously we learned how to determine the quadrantal angles. So I'm going to use the quadrantal angles as reference points to determine the position of the other angles. So let me list the different quadrantal angles. We start with pi over 2. Pi over 2 is equivalent to a 90-degree angle. Then we have an angle measuring pi radians. That's equivalent to a 180-degree angle or a straight angle. Then we have 3 pi over 2, which is equivalent to 270 degrees angle. And then we have 2 pi. So when the terminal side makes one full rotation or one full revolution, then it is an angle measuring 2 pi radians, which is equivalent to 360 degrees. Now, another important thing to note here is whether the angle is a negative angle or a positive angle. The angle given to us is theta equals negative pi over 4. When the angle is negative, then the rotation of the terminal side is in the clockwise direction. So for negative angles, we have to rotate the terminal side in a clockwise direction. If the angle given to us is a positive angle, then the rotation would be in the counterclockwise direction. So we have to keep that in mind when we are drawing the angle. Alright, so this is a negative angle. We are going to start from the initial side, which is always positioned along the positive x-axis in standard position. So this is the initial side resting on the positive x-axis, and we have to rotate in the clockwise direction because this is a negative angle. But by how much should we rotate it? If we are rotating in the clockwise direction, then negative pi over 2 would be right here. Okay, so this would be negative pi over 2 rotating in the clockwise direction. Now, pi over 4 is exactly 1/2 of pi over 2, correct? So 1/2 of pi over 2 is pi over 4. I'm using this quadrantal angle of negative pi over 2 as a reference point, and since pi over 4 is exactly half of pi over 2, the terminal side is going to be positioned midway between the positive x-axis and the negative y-axis. So let's go and draw it. We are turning in the clockwise direction, it being a negative angle, and we turn exactly midway between positive x-axis and a negative y-axis, and this angle between the positive x-axis and the terminal side is negative pi over 4. All right, I'm going to pull up the solutions now to see whether we've done it right. They may have done it a little bit differently, so let's go for it. It says the angle is negative. It is obtained by rotating the terminal side clockwise, and that's exactly what we did. This is the initial side. We have to rotate it clockwise, correct? And then it says we rotate the terminal side clockwise 1/8 of a revolution. So they've done it a little bit differently. I used the quadrantal angle of negative pi over 2 as a reference point and drew the terminal side exactly midway between the positive x-axis and negative y-axis. What they did was they determined positive pi over 4 to be 1/8 times 2 pi. That means 1/8 of 2 times pi. Based on that, they drew their diagram. So let me pull up their diagram that they did. So here we have the vertex should always be at the origin, and then the terminal side is drawn with this red arrow, right? And it gives us angle theta equals negative pi over 4. Now in this example, we've been given a positive angle, alpha equals 3 pi over 4, that we have to draw in standard position. Now, this being a positive angle, we immediately know that the terminal side has to rotate in the counterclockwise direction to form the angle, correct? Because when the angle is positive, the terminal side rotates in the counterclockwise direction. So that being given, we have to now determine by how much should the terminal side rotate. Again, I'm going to use the quadrantal angles as reference points. Over here, we have 0 degrees or 0 radians to start with. Then this is pi over 2. Right? When the terminal side is on the positive y-axis, it forms pi over 2 radians. Then we have pi over here on the negative x-axis, 3 pi over 2. And then when the terminal side makes one full rotation or revolution, it forms an angle measuring 2 pi. So 3 pi over 4 is 1/4 less than pi, correct? So let's do it this way. Think of pi being 4 over 4 pi, correct? 4 over 4 pi is what pi radians is, and 3 pi over 4, it's just pi over 4 units less than pi, right? So when we draw the angle, we will start from the positive x-axis or the initial side, and then the terminal side has to rotate in the counterclockwise direction and come to stop right here midway between pi over 2 and pi. Let me just draw it a little better. We move in the counterclockwise direction and come to rest exactly midway between pi over 2 and pi, and that would be 3 pi over 4. So it's this angle which is positive 3 pi over 4. All right, now we shall try to draw the angle negative 7 pi over 4 in standard position. The negative sign to the angle measure tells us that the rotation of the terminal side is in the clockwise direction from the initial side. So it's going to turn in the clockwise direction. That's what the negative sign tells us. The rotation or the revolution is going to start from the initial side and it's going to be in the clockwise direction. So now we have to figure out where the angle would be located, where the terminal side would come to a stop based on the measure of 7 pi over 4. What I'm going to do here is to use the nearest quadrantal angle to determine the position of the terminal side for this measure. Now 2 pi is a complete revolution or a complete rotation. So if we started from the initial side, moved along the clockwise direction and came back to the initial side, we would have formed an angle of 2 pi radians. 7 pi over 4 is the angle that we are concerned with, and that is pi over 4 units short of 2 pi from the clockwise direction, correct? How do we know that? 2 pi can be rewritten as 8 pi over 4. And from it, if we subtract 7 pi over 4, it's pi over 4 units less than a complete rotation. So if we go around in the clockwise direction and come to a stop exactly pi over 4 units short of 2 pi, pi over 4 units short of completing the circle, then we would have formed an angle of negative 7 pi over 4. And that's exactly what I'm going to do. Let me delete this and redraw the angle negative 7 pi over 4. So I'm going to go in the clockwise direction and stop pi over 4 units before completing a full rotation. So it's going to be located somewhere exactly in between the positive y-axis and the initial side. So now we have formed an angle of negative 7 pi over 4. All right. So this is how you're going to go about drawing different angles of radian measures. You have to look at the sign, whether it's positive or negative, to decide in which direction the rotation is going to occur, and then you can use the closest quadrantal angle as a reference point to determine the location of the terminal side forming the angle. All right, so I'm going to pull up the solution. They work it a little bit differently from the way I work it, but it should give us the same answer. All right, so here it says the angle is negative. It is obtained by rotating the terminal side clockwise, and they've taken the absolute value of negative 7 pi over 4, and they show that negative 7 pi over 4 is 7/8 of 2 pi. All right, so in order to get that angle, we rotate the terminal side clockwise 7/8 of a revolution. So this angle is also 7/8 of a full revolution. And then they have shown the vertex over here. This is the vertex of the angle, and they refer to the same angle, which is negative 7 pi over 4. All right. Now we are going to look at drawing an angle which has a measure greater than 2 pi. That means in order to draw this circle, we have to rotate more than a full circle, more than 2 pi units. All right, 13 pi over 4. This being a positive angle tells us we have to rotate the terminal side in the counterclockwise direction, but by how much? In order to determine that, whenever the angle measure is greater than 2 pi, just subtract 2 pi or multiples of 2 pi to determine how much we have to go over the 2 pi. So I'm going to take the 13 pi over 4, and from it I'm going to subtract 1 times 2 pi. So 2 pi can be written as 8 pi over 4 when we give it a common denominator of 4. And what will we end up with? We will end up with 5 pi over 4. And 5 pi over 4 is the same as saying 1 and 1/4 pi. So we have to complete a full revolution come to 2 pi, and then we have to go another pi and another 1/4 pi to be able to draw our angle. Let's first come around a full circle at 2 pi. All right, when we come full circle, we have covered 8 pi over 4, which is the same as 2 pi, correct? And now we have to go another 1 pi first, and this gives us another 1 pi, and it brings us to 12 pi over 4. So this revolution here going all the way and then coming back to the negative x-axis, completing another pi over the 2 pi is 12 pi over 4. We have to go another 1/4 pi to get our angle, correct? So 1/4 would be somewhere in between the negative x-axis and the negative y-axis. So let's go around here. So that's another pi over 4 from the negative x-axis to get us 13 pi over 4. All right, so I'm going to delete this now and show it with one arrow instead of so many different arrows. It's going to start in the counterclockwise direction and then go all the way around and come and stop here. So this angle measure is 13 pi over 4. All right, so let's see what they have come up with in the solutions. So it says the angle is positive. We have to move in the or rotate the terminal side in the counterclockwise direction, which we have done. And then 13 pi over 4 is 13/8 of 2 pi. Therefore, we rotate the terminal side counterclockwise 13/8 of a revolution. We get the vertex positioned here. Of course, vertex always has to be located at the origin, at the point of intersection between the x and y axis whenever an angle is in standard position, and then we have the angle drawn here. It's slightly off because I drew it by hand, so it's not properly scaled. I can redraw it over here. So this is our angle. All right, now we'll try to understand what coterminal angles are. This is a concept especially for angles in the standard position. All right, it says here two angles with the same initial and terminal sides but possibly different rotations are called coterminal angles. So the angles, or any number of angles that have the same initial side and the same terminal side, are known to be coterminal angles. So just to exemplify this, I'm going to draw an angle here on the xy coordinate plane. Again, any angle in the standard position will have its vertex located at the intersection between the x-axis and the y-axis, and the initial side will lie on the positive x-axis, and the terminal side, let's draw the terminal side somewhere here, and let's try to figure out the coterminal angles based on this position of the initial side and the terminal side. All right, so I'm going to write here, this is the initial side of the angle, this blue arrow, and the green arrow is the terminal side. So the first angle that we can see is, let's say, this direction. If we rotate the terminal side in the counterclockwise direction, it will form a positive angle, and let's say this rotation forms pi over 4 radians. So pi over 4, let's say that's the angle measure when the terminal side moves in the counterclockwise direction and comes to a position here. It forms an angle of pi over 4. Now let's try to look at another angle that can be formed with the terminal side located at the same position without moving the terminal side. If the terminal side were to rotate in the clockwise direction, then it would form a negative angle. And let's say it came to rest at this very same location, then what would the angle be? Because the rotation is in the clockwise direction, it would be a negative angle, and it would be 7 pi over 4. So if you're moving in the clockwise direction and come to stop pi over 4 units short of 2 pi, then we form negative 7 pi over 4 radian measure angle. All right. So that's another angle here, and they are coterminal angles simply because they share the same initial and the terminal side. If we moved in the counterclockwise direction and came all the way around, came to stop at wherever the terminal side is located, then it would be 2 pi plus pi over 4, correct? So we completed 2 pi here, and then we moved another pi over 4. So that would be 9 pi over 4. This rotation gives us 9 pi over 4 positive angle. So 9 pi over 4. That's another coterminal angle. And we can keep going. We can keep rotating and come up with different coterminal angles for the same angle pi over 4. So pi over 4, negative 7 pi over 4, 9 pi over 4. And if we keep rotating and come to stop at the same terminal side without moving the position of the terminal side, then we will come up with vast number of coterminal angles. All right. Now let's understand how we can find the coterminal angle of a given angle. First of all, if the angle is given to us in degrees, then we add or subtract multiples of 360 degrees. 360 degrees is the angle of a complete circle. If the given angle has gone over 360 degrees, then we have to multiply the 360 degrees by an integer value. That means we will have to add and subtract some multiple of 360 degrees, in other words. If, however, we are given the angle measure in radians, then we have to add or subtract multiples of 2 pi, 2 pi being the measure of a full circle. So let's say that we have been given an angle measure of 840 degrees and we are asked to find the coterminal angle for it. 840 degrees is clearly more than 360 degrees. 360 degrees is one round, and then another round is 720 degrees. 840 degrees is less than 3 rounds, however, so we will subtract from 840 degrees 2 times 360 degrees. So that will be 840 minus 720 for an angle measure of 120 degrees. That means 840 degrees will be located somewhere here, the terminal side. So this is an 840 degree angle, positive angle, which is equivalent to or which has a coterminal angle of 120 degrees. Without going in circles, the angle 120 degrees is a positive angle. It has the same initial side as well as the same terminal side as 840 degrees. Therefore, we call them coterminal angles. All right? Now let's look at these examples here to find coterminal angles for the angles given to us in degrees. The first one is 400 degrees. Now when the angle is a positive angle, then we must subtract multiples of 360 degrees, right? 400 degrees has gone over 360 degrees once. Correct? So we are going to do 400 minus 360 degrees for a coterminal angle of 40 degrees. As simple as that. For B, which is negative 135 degree angle, because this is a negative angle, we will need to add 360 degrees. Now, negative 135 degrees is within the 360 degree angle, correct? So we're just going to do minus 135 degrees, but this time add 360 degrees to it to get the coterminal angle. I'm going to pull up the solutions. So 400 degrees minus 360 degrees is 40 degrees is what we got. And then we have minus 135 degrees plus 360 degrees, which is 225 degrees. So the coterminal angle for a negative 135 degrees will be 225 degrees, whereas for the 400 degree angle, its coterminal angle is 40 degrees. To find the coterminal angles for angle measures in radians, we perform the same procedure, but this time we will be adding or subtracting multiples of 2 pi from the given angle. Again, if the angle is a positive angle, we will subtract 2 pi or multiples of 2 pi. If it's a negative angle, we will add 2 pi or multiples of 2 pi. All right. The first one given here is 13 pi over 5. 13 pi over 5 is more than 2 pi, correct? It has gone over 2 pi, correct? 10 pi over 5 is 2 pi. And then it has gone 3 pi over 5 over the 2 pi. So if we subtract from that 2 pi, what we will get is 3 pi over 5. So the coterminal angle for 13 pi over 5 is 3 pi over 5. For negative pi over 15, it's again the same procedure, but this time we will be adding 2 pi just because this is a negative angle. So negative pi over 15 plus 2 pi is equal to negative pi over 15 plus 30 pi over 15, correct? Which gives us 29 pi over 15. Right, so let's go ahead and check the answers. Here they have 13 pi over 5 minus 2 pi equals 13 pi over 5 minus 10 pi over 5, which is 2 pi with the same denominator, which gives us 3 pi over 5. Correct, exactly what we found for our answer. And then minus pi over 15. Let's pull up the answer for that. It's negative pi over 15 plus 2 pi is negative pi over 15 plus 30 pi over 15, and when we perform the subtraction, it's 29 pi over 15. All right, now I call this subtraction because minus and plus ends up being a subtraction, correct? Now we will end the lecture on this chapter by talking about an application of the arc of an angle. We will learn how to find the length of a circular arc. It says, let r be the radius of a circle and theta the non-negative radian measure of a central angle of the circle. The length of the arc intercepted by the central angle is S equals r times theta. So what we learned previously was that the radian measure of an angle theta is S over r. And using that equation, we can solve for any of the variables, provided that the other two variables have been given to us. All right, the other two variables have values to them given to us. Solving for S, which is the length of the arc that is intercepted by the central angle, all we need to do is solve for it, right? So if theta equals S over r, then S is going to be just multiply both sides by r, and we will end up with the angle measure theta times r. All right, so this is the formula we can use to find the length of a circular arc using the formula that we learned for the radian measure of an angle. Let's go through an example to find the length of a circular arc. The question here says a circle has a radius of 6 inches. Find the length of the arc intercepted by a central angle of 45 degrees. Express arc length in terms of pi, then round your answer to 2 decimal places. So the first step in this exercise in solving the problem is to convert the angle measure given to us in degrees to radians. The question says express arc length in terms of pi. So the angle measure given to us is 45 degrees. We have to convert that to radians using the process that we learned to convert from degree to radians. We take the 45 degrees, multiply it by pi over 180. We get 45 pi over 180, which when reduced gives us pi over 4 radians. Once we complete the conversion, we are ready to use our formula that S equals R multiplied by theta, derived from the formula theta equals S divided by R. So here's our formula, S equals R times theta. Let's plug in the values in there. R has a value 6. It says up here a circle has a radius of 6 inches. So plug in the value of the radius for R, and then theta is pi over 4. It is the converted angle measure, the angle measure that we converted from degrees to radians, and when we do this multiplication we should come up with 6 pi divided by 4 inches, which when reduced gives us 3 pi over 2. When you run this through your calculator, the length of the intercepted arc should be 4.71 inches. Therefore, the length of the arc intercepted by a 45-degree central angle in a circle of radius 6 inches is 4.71 inches. All right?